Alright, so I think we've done all the medium difficulty problems. Let's switch to the slightly more challenging, harder ones. They're not tremendously, they're actually about the same level as the medium ones, not tremendously more difficult. But we're combining multiple chapters here, and that's kind of cool. It's a good way to learn and review these reactions. Let's try it out. We'll start on problem M. We'll do it on my paper, but let's just look at it real quick. What's going on with M? It looks like you got a tert-butyl group, and there's the tert-butyl group, and then somehow we're adding this part. It looks like we also have an ether, so we're doing an ether synthesis. So we're probably going to attach the methyl ether as well. But that's all there is to it. It's a pretty straightforward problem. Let's see if we can get through that now. I'll redrive. M. Question mark. Alright, so we're doing tert-butyl, O, CH3, cyclopentane, and it looks like we're attaching there, and we're also attaching there. And usually in an ether synthesis like this, we'll do the ether synthesis last, so I'll just do it from the alcohol. We saw this kind of problem just a while ago, so same thing, just envision the alcohol. Starting to make it from the alcohol. So what's the alcohol look like? From the alcohol. How do you do a Williamson ether synthesis? It's a 1-2 thing. First a base, NaH, then a methyl iodide, probably, or bromide. The methyl iodide is a liquid, methyl bromide is a gas. Not a huge distinction. It's not something you really care about, but in the real world we always use methyl iodide or iodomethane. Okay, so where's our other squiggly? Looking back to where we're going, it's this tert-butyl thing, and probably got to make it from this bond. So, and if we just apply a Grignard in reverse, it'll get us where we want to go, right? So, assume that the this will be a nucleophile, the Grignard part. That'll be the Grignard part, tert-butyl Grignard. Here, this squiggly is on the neighboring carbon from the OH. So it's probably going to be this, but in an epoxide form. Right? So it might look like a Grignard, a tert-butyl Grignard, MGBr. And it looks like that, but it's an epoxide. So it's essentially going to be a 5-member ring, carbon, epoxide. I'll put it up here, I guess. There's step 1. It'll look exactly like that, but as an epoxide. So it would be epoxide, 5-member ring, and then water. Cool. Now we've got to get this guy to be a Grignard, and so maybe do that from the bromide and the magnesium. Now, how do you go from an alkane to a bromide? Chapter 3, long time ago. It's a Br2 and heat or light. And that would make the tertiary bromide. So M's not that bad. I think the hard part, I mean, this is combining a lot of chapters, right? The ether synthesis, chapter 9. The Grignard was chapter 8, but attacking an epoxide, that's chapter 9. This is chapter 3, so yeah, we got a couple chapters in there. Let's try problem N now. What's problem N? Let's see, let's take a look at N. Problem N, it looks like you got an alcohol with a cyclobutane, 2 carbons OH. I can kind of see that here, cyclobutane, 2 carbons. It looks like we're cleaving right, or we're forming that bond. Not exactly sure how we're going to do this. I can't just magically say, oh, I know what it is. That's why we do retrosynthesis, right? We're going to go backwards and see where it takes us. The only goal is to eventually work our way back to this. But that's a very easy connection. That's a Grignard right there. I think it says, the hint is it's actually pretty easy. So, we'll see. We'll see how easy it is. Problem N. Okay, so we're starting from cyclobutane, 2 carbons OH. We're ending with cyclobutane, 2 carbons OH. Okay, let's see if we can do it. I mean, the squiggly, where's the squiggly? It looks like the squiggly is right there. Yeah. And we can do that easily from a Grignard. Grignard on the left. So cyclobutane, carbon-carbon, Grignard. And then squiggly's next to the OH, so then it's a tertiary alcohol. So it's what? Formaldehyde, aldehyde, ketone, or epoxide. It's looking ketone, like a ketone, right? Like a ketone that would give you a tertiary alcohol, like that. So maybe all we gotta do is start from the Grignard, OGBR, 1, 2. And what's in our electrophile is a ketone, cyclopentanone. Cyclopentanone water. And you're golden. That carbon attacks that carbon, makes that. Okay, now how do you make a Grignard from the bromide? With Mg. How do you go from an alcohol to bromide? Best way, don't say HBr. HBr can work, but you sometimes get rearrangement behavior. So the best way is PBr3. What if you want to go for the chloride? If our goal is a chloride, you could use SOCl2. Interestingly, let's just pretend we did that, because you can do that actually too. It would be SOCl2, and that is the best way to convert an alcohol to a chloride. And then Mg would happen, and you'd make MgCl, but that's actually totally fine also. We just haven't really emphasized that. Whoops. Got a little mess there. So MgCl is fine for Grignard also. I think, generally speaking, we do it with MgBr, but that works too. SOCl2 is the way to go from an alcohol to chloride. Problem N. Oh. Problem O now. Looks like, 5 carbons there. It's a terbutyl with an extra carbon. Bromide is 5 carbons. I can see them right there, and the squiggly looks like it's right there. This is almost too easy to do. It's just going to be make a Grignard from the forward direction. Make a Grignard, and then a 2 carbon electrophile. This can be an epoxide, a 2 carbon epoxide. And then make a methyl ether. At the very end it would be sodium NaH and then CH3I. So I'm not going to do that one. It's too easy. Problem P, I better do. But essentially you're just going to, for problem P, you're going to make that bond between the benzene and the other 6-member ring. And then all you got to do is get it ready for a dibromination, which is one of the weird chapter 12 reactions. So let's say how to make a 1,2 dibromide. Do it backwards, and that's a chapter 12 reaction. So you just do it from an alkene. Let's try it out. Problem P. So we did O, too easy. P. Is iodide, iodobenzene, and then it's going to be BrBr. Okay, so to make a BR-BR, it's just from an alkene, so we just draw the alkene. And what's the reagent? It's BR-BR, BR2. It's the dibromination of an alkene. It's a kind of poorly drawn alkene, but I can't, yeah. That's fine, that's better. Alright, cool. And it's BR, it's the bromonium ion thing, so the alkene attacks BR, you make a bromonium, a little three member ring, and the other BR attacks it. Okay, so then where are we going? Iodobenzene, so probably gotta make this bond. Gotta make that bond. But you can't do it directly, and remember, we can't do it in a way that gives us an alkene out. So we gotta make it from an alcohol, right? So we can make an alkene from an alcohol. How? It's a non-nucleophilic acid, so H2SO4. H2SO4. Now we're very close here. All we gotta do, oops, benzene. All we gotta do is build that bond, and we can do it from a Grignard. We can also do it from organolithium. Let's change it up and do an organolithium, and it would be from, we'll say, phenylithium. 1, 2. So which electrophile? It's squiggly is right next to the alcohol. It's a tertiary alcohol, so it's a ketone. That'd be the cyclohexanone, the ketone. Great. I can draw. Oh, here. There's my 1. There's the ketone. 1, 2 is the water. A little scrunched up. Alright, and then to make the iodo to the lithium, you just add lithium. And we're good. That's problem P. Now problem Q is really fun. And it's almost the same problem. The only difference is instead of make a BR-BR at the end, you make it with OH-OH. So we're going to approach it the same exact way, but I can just solve it right here. The last step is different. So you go from the alkene. Let's draw the alkene. Five-member ring, and we'll just draw the alkene. So you can make the alkene the same way we just made the other alkene in the last problem. But then the question is, how do you do the OH-OH thing? It's just a different chapter 12 reaction. Anybody remember what it was? It began with O, and it's not ozonolysis. It's not ozonolysis. It was a heavy metal that began with O. Osmium tetroxide. So it's OSO4. And it's like Na2S or H2S. Osmium tetroxide makes alkenes into dialcohols like that. Otherwise, it's all the same as the last problem, except you use a 5-member ring ketone. We did them all. Hopefully that's helpful. It's a good way to review all the reactions. Alright, good luck.